S-box entries. For n, 8,8,2, convolutional code, using 2-bit shuffling boxes, there are 16 S-boxes or keys. For higher n-bit shuffling boxes, the number of keys increases. For example, 8-bit shuffling boxes will give 28 keys. The 4 2-bit S-boxes used to illustrate the scheme are shown in Table 1. Given an 8-bit data sequence as, the lookup S-box, sub 1, 1 is used to shuffle the first pair of bits, sub 1, 2 is used to shuffle the second pair, sub 1, 3 is used to shuffle the third pair, and sub 1, 4 is used to shuffle the last pair. 2-bit shuffle lookup table. P-box entries. The interconnections between inputs and outputs are implemented using a permutation set lookup table. For n, 8,8,2, code, the 808, inputs and outputs could be permuted or interconnected in at least 77 equals 823,543 ways. A permissible permutation is shown in Table 2. Input-output interconnect lookup table for encoder. After the specification of the keys, the vulnerable convolutional code block will be cascaded into different stages using the product ciphers obtained from the S-box and P-box. Using 2 stages, a nonlinear, 2 cascaded is as shown in initial structure of the cascade before encoding. N, sub 1, 1, sub 1, 2, sub 1, 3 and sub 1, 4 are S-boxes used for pairwise bit shuffling and the input vector to the first transducer. X7, X6, X5, X4, X3, X2, X1, X0, is the output set from the subband encoding block, while the output vector, Y7, Y6, Y5, Y4, Y3, Y2, Y1, Y0, is the ciphertext from the second transducer stage. It is worth noting that the security level could be greatly increased by increasing the number of stages to be cascaded. Residue number system, RNS. The residue number system uses the Chinese remainder theorem, CRT, to compute unknown values from the remainders left or residues when unknown values are divided by known numbers. The modular Chinese remainder theorem states that assume M1, M2, Mn are positive integers, relatively prime pairs, me, Mk, equals 1 if I hash k. Let B1, B2, Bn, be arbitrary integers, then the system of simultaneous linear congruence has exactly one solution modulo the product M1, M2, Mn. The solution to the simultaneous linear congruence is formally given as where Mj equals Mgen equals J equals 1 in Mj. 8. Establishes the uniqueness of the solution. In this research, the integers Tj equals Xj often referred to as the multiplicative inverses of Mj are computed a priori by solving the linear congruence in 7. In other words, if Mj equals M/Mj, then the multiplicative inverses, Tj are computed by solving the congruence Tj Mj equals 1, mod Mj.